Welcome back, students. In this video we will talk about realization of half adder using NAND gates only. If you look into the previous videos of half adder, we derived certain equations of sum and carry. The sum equation was given as A XOR B and carry equation was given as A and B dot product. Means we were using XOR gate here and we were using AND gate over here. And if we talk about a realization with basic gates, this XOR gate can be further you can say derived with AND gate, OR gate and NOT gate. Now what is the purpose of using a universal gate, suppose NAND? So for that we should know the concept of universal gates. So there are two types of universal gates, which are NAND and NOR. And the reason why we use universal gates is, first of all, we can implement any function using them. We can implement any function using universal gates. So it means that if suppose we talk about the NAND gate, the same NAND gate can also function as AND, OR, NOT, XOR, XNOR as well as NOR. Means all the remaining gates can be derived from the NAND gate, and the same is true for the NOR gate as well, as we shall see in the next video. But today our focus is NAND gates. So the aim of today's topic is these gates, these different gates that are being used over here, we will replace all of them with a single gate, and that gives us the other advantages of universal gates, like suppose availability. Suppose we are going for a market and we are looking for the ICs of all these gates. So it may be a possibility that some of the gates are not available, so that will hinder our working. So if we are having a universal gate, all you require is simply one particular IC and all the functions can be implemented. And one more advantage of using universal gates would be the flexibility that it offers to you. The flexibility in a sense that if suppose tomorrow our logic function is getting changed, equations are getting changed, so it might be a possibility that we don't need AND gate, we rather need only OR gate. So the same AND gate IC cannot function as OR gate, or OR gate IC cannot function as AND gate. That is not possible. However, if we are having a NAND IC, you can take any function out of it. It can work as NAND also, OR also, XOR also, anything. So that means there is a lot of flexibility involved in it. So due to all these reasons, when we look at the practical sense, we would prefer using universal gates rather than the basic gates. So having these concepts clear, let us discuss these equations and let us reframe the equations of sum and carry so that we can implement this using NAND gates. We will start with the sum first of all. So if we talk about the sum equation, we can write it as it is A XOR B, so it can be written as AB bar plus A bar B. Now what we will do is we will write that sum can also be written as AB bar plus A into A bar. So A into A bar is 0, so that will not affect our equation, plus A bar B plus B into B bar. So if you will look at the two terms that have been added over here, their dot product is 0 because they are complements of each other and one of the terms has to be 0 obviously. So anything multiplied with 0 has to be 0. So that's why it will not affect our equation. It's like you are doing x plus 0, that is again x. Now what we will do, if we look at these two terms, we can take A common out of it. So it will be A bar plus B bar. Similarly, out of these two we can take B common, so it will be again A bar plus B bar. Now there is something called as De Morgan theorem. So according to that, if we are having A bar plus B bar, this is equal to A dot B whole bar. So what we can do here, we can write this sum equal to A, then in brackets we can write A dot B whole bar. Similarly, we can write B, then A dot B whole bar. and we can reframe this and we can write it in the form of a dot a b bar, then this plus we will change to dot, then we will write b dot a dot b bar. And now what I will do, I will introduce bars like this. So this is the bar and there is one whole bar. Now what is happening in this last step, this last step is actually the same thing that is represented here, because if we will use this De Morgan theorem here, okay, just to prove our point, so it will be what, it will be like a dot a b bar, then double bar plus b dot a dot b bar, then double bar. And we know that if there is a double bar, if it is like x double bar, that is equal to x. So we can say two bars will cancel each other. So these two bars will cancel, these two bars will cancel. So what actually you are getting is the same two terms which are available in our second last step, right? So that means whatever is written in this last step, let us highlight this, this one, this is the equation that I will be using while implementing the things with NAND gate, and this is only for the sum. Now let us do it for carry also. Carry one is easy. Carry is simply a dot b, which is an AND gate, so we can write it as a dot b, then bar and bar, double bar, and I said double bar can be cancelled, right? So it is like a dot b bar we will implement with a single NAND gate, and then we will do NAND gate with bar. So we will now see in our next slide how can we use these two equations to implement overall diagram of half adder using only NAND gates. Now we have just noted down the equations we got for sum and carry. Let us now draw our logic diagram. So first of all we will implement is a dot b whole bar, okay, because we can see it implemented here also. We are having a dot b whole bar here also and here also. So let us try to do it with the NAND gate. So we will draw first NAND gate. So this NAND gate we will give two inputs, and these two inputs we call as A and B. So this output is A dot B whole bar. Then what we will do, we will give this NAND gate output to two different NAND gates. So these are two more NAND gates we are drawing, and now what we will do, this A we will give here, this B we will give here. Now please note down, this is A, this is B, and this A dot B that we are having here is given as one of the inputs. So what is the output here? You just multiply the two inputs and have a bar. It will be A dot AB bar whole bar. So what we are actually getting is this part of the equation. Similarly, what is this particular, the second one? It is B dot AB bar whole bar. So what is this output? This is the second part of our equation, right? Now what is our next step? Once we got both these inputs, then we can see there is one more bar. So it's like two inputs with the bar. So it is again a NAND gate actually. To implement this we need one more NAND gate. So what we will do simply is we will have these two lines, it will be given to the next NAND gate. Now this NAND gate will implement overall function whatever we have written here. So this will be nothing but your sum. Now carry is easy because I told you carry is what? It is A dot B double bar. So A dot B bar is already available. Where is A dot B bar? It is here. So what we need to do is just give it to a NOT gate. And how do you implement this using NOT gate? NOT gate means single input. So we have to short two input terminals of a NAND gate. So if this is A dot B bar as an input, so this output will be A dot B bar with one more bar, and bar will cancel. That will be A dot B, and that will be nothing but your carry. So we will write here this is our carry. So in this way we have implemented half adder with NAND gates only, because now if you will realize this logic diagram, of half adder, we are using only and only one type of logic gate, which is NAND. And one very important question that often comes in the competitive exams like GATE and all is they will ask you how many number of NAND gates are required to implement half adder. What is the minimum number of NAND gates required to implement half adder? And the answer is 5. We are using 5 NAND gates as is visible in the diagram, 1, 2, 3, 4 and 5. So that's it for today's video. In our next video we shall talk about realization of half adder with NOR gate, as that is again one of the universal gates. So till then, God bless you all and have a nice day.